はい。 已解锁，请启出话筒。
再累
今天
啊？
今天有吗？是今天。
今天、明天呢？OK，再读一天。OK， maybe we can start now. Let's recap some important points from last week. So maybe first question, when do you use induction? When do you use induction proof? When do you use induction proof? When do you use induction proof? Any idea? What's the induction proof? Do you still remember? What are the three main steps you have? You need to prove for base case, and then assume inductive hypothesis, and then you prove your inductive step. Right. Okay, so what's the purpose of doing these three things then? Yes, X in where? In where is very important. You want to prove a statement that is true for all X in N. Right. Why is it useful here? If you imagine that if you want to prove for all X in N, what are the things in N? N is what? You remember? In this class, you have to remember what's N. Natural number. 1, 2, 3, 4, 5. If you want to prove one by one, how many you need to prove? Infinitely many. So how do you settle infinitely many cases? So we use this three steps to settle the infinitely many cases, right? Because we start from base case, okay, 1, and then inductive hypothesis. If you start at any places, I prove that the next one is true. So that 1 is true, then 2 is true. If 2 is true, then 3 is true. 3 is true, then 4 is true. So this kind of inductive step usually works when if you prove for any n, the method is the same, or depending on the previous n. Okay, so that you don't need to repeat calculation for every one of them. Okay, so you just start anywhere. Okay, so this is for proof part. Second part is real number. So I want you to invite you to think about this story here. Okay, how to think about real numbers here. So remember we'll start with n, right? And then we build rational number. No, before rational number, we have integers. Okay. So when you think of natural number, how do you think of it? Just now I wrote down for you, right? Like 1, 2, 3, right? Okay, it's kind of discrete. You know what discrete is? Like you are discrete. Okay. You and your friend got a distance, right? Then what is that? Last time we say that we add in the additive identity, and then also the additive inverse, right? Something like that. Okay. Something like that. And then we add in the multiplicative inverse, right? For rational number, if you still remember m over n, right? We define as m times n inverse. So they are like 1/2 here, maybe 1/3 here, negative 3/3, maybe 1/3. And then I tell you that this is a field. Do you still remember what a field is? I can compose them. Okay, I can compose them. I can. What can I do? I can add them. I can multiply them. Here you can see this addition and multiplication seems like similar symbol. You just twist it a bit. Twist it 45 degree maybe, right? So it's really similar. So you can multiply. So maybe let's take some non-trivial multiplication here. So maybe you multiply to 6, and then maybe you add to 5, right? So you can add to 5. So far, okay? Right. Yeah. So what's we're gonna do today is we're gonna put in order. Okay, we're gonna put in order. Actually, it's a total order, so that we can compare everything inside this picture here. Okay, for now, you can think of it as a discrete thing, the number. Okay, I can understand what I think. 全部 okay 吗? Just come to the okay. Yeah, feel free to ask. Okay. Right. So today we will introduce order on it, and then slowly we can see that it constitute a line, and then this line is no longer as discrete as you think about it. Okay. Then it will reach what you learn about, like you will draw your number line like this, right? Like for example, in your calculus, you will draw something like that. Okay. Um. Cool. Okay. Before we jump into today's lecture, something on your tutorial stuff. So you can start. I already posted out the tutorial if you can check it on week 1, right? So this week we're gonna start with tutorial 1, and the tutorial mode is the first, second, 30 seconds, 30 minutes. You will form groups, maybe 3 to 4 person. You will discuss question, and then the last 20 minutes we will have presentation. Okay, so this presentation will be included in your marks. So the ideal case is you volunteer yourself, okay, because everyone will take turns one, no worries. You must have your turn one. So be sure that you can pick your own favorite question, then you can present. So each day, I mean, maybe I will fix 2 questions, then when you discuss, after you discuss, you can present. Because in your class, you have like 13 person, right? So we have 13 week as well. Is it 13 week? Yeah, 13 weeks, 14 weeks. No, last week already missing one, right? So we still have 13 weeks. So each one will get presentation once, actually twice, because each time we have 2. So you can refresh your marks, basically. So first time if you don't do well, second time you can do better. So you can do it second time when everyone finish their turn. Okay, if not, if no volunteer, then I have to pick. Yeah, no choice. But then the ideal case is you volunteer yourself. Okay. And then we will have a tutor to help around as well. Basically, your senior. Okay. Okay. So that's it. For the quizzes, right? Please bring some pen to the class. I'll give you paper. Maybe bring 2 different color pens, but not red, because I want you to like mark each other question. Learn to read solution. Okay, obviously I will mark it, but then we'll discuss solution in class. Does it make sense? Okay. Yeah. We will do it tomorrow. So one more day for you to do revision or ask question. You can ask in Moodle, by the way. Okay. So let's start today's class. So we'll start with orders. Okay. So let's have some order axioms here. So order axioms here, we want to make sure that our real number is an ordered field. Okay. So let's take the 3 number in real number. Okay, so what are these axioms? So the first axiom is called trichotomy. Okay. Do you have idea what trichotomy is? Tri is like 3 things. Okay, so triangle, okay, tricycle. So what are the 3 things? So This three things, only one of them has to be true if you compare two numbers. All right, either a less than b, or a equals to b, or a greater than b. Only one of them can be true. So if you take two number, take it out, one of them must be less than the other, or they are equal. Does it make sense? Okay. Okay, so this is trichotomy. The other is order preserving. Okay, so order preserving meaning you need to preserve the order. Okay, so how to preserve the order? So under what operation you preserve the order? So if you know that A is less than or equals to B, so okay, maybe I should define here. So we define less than or equals to as less than or equal. Okay. Or either two of these things happen, this will implies that A plus C less than or equals to B plus C. Okay, for any C. Does this match your high school calculation? Does this match? Like if you know 2 less than or equal to 4, then whatever you add to both sides, the order still preserved. No matter positive, negative, 0, you add. Good. So we take it as an axiom. Second is if you have C greater or equal to 0 as well, then you will preserve the order in the sense of multiplication. Remember, I think you got told in high school that if you multiply negative number, the sign change, right? Okay, later we'll prove that. And then the rest are just relation. Okay, reflexivity, anti-symmetry, and transitivity. Maybe someone can tell me what's reflexivity I should put here. Reflexivity means what? You relate to yourself, right? Okay, how do you relate to yourself here? What do you think? Control. What? What do you mean control? Copy paste, copy paste, copy paste what? Copy paste what? Huh? What do you mean? You reflect on yourself? Oh. Okay. So which one? which relation I should put here? Okay, think. Okay, something in between A lah, right? Something in between A. I mean A equals to A. I think this one we know already. Okay, but then now we are talking about less than or equal to actually. So meaning, so this just means that this just means what? This just means A is less than A or A equals to A. Which one is true? What do you think? Huh? I don't know. See, like, no. From here. So this is a statement, right? Okay. So I say that this is a true statement, right? So one of them have to be true, right? So which one is true? Second one is true. The first one, false, because of the trichotomy law. Okay, because I already know A equals to A, so the other cannot be true anymore. But then I still can write this down, right? Because true or false is true. Doesn't matter. Okay, doesn't matter. Okay, how about anti-symmetric? Can you recall what is anti-symmetric? Symmetry is what? A less than or equal to B, B less than or equal to A, then A equals to B. Wait, no. A less than or equal to B and then B less than or equal to A. This is symmetric. But anti-symmetry, if A less than or equal to B and B less than or equal to A, this just implies that these two things has to be the same. This is anti-symmetry. Okay, so anti-symmetry is if you swap position, both of them are true, then it is the same thing. Symmetric is if A less than or equal to B, then B less than or equal to A. Transitivity, A less than or equal to B and B less than or equal to A, C, sorry, then A less than or equal to C. So far, okay? So far. Actually, anti-symmetry is the one that we use the most. when you want to prove something, two numbers are equal, you just show that A is less than B, B is less. When you want to show A and B are the same. Okay? Okay, good. Next, we'll define something called the positive number. Maybe you might think that this is quite trivial. Maybe let me write down first. So what are the positive number here? Let's denote as R greater than 0. So these are all the real number such that it is strictly greater than 0. And then the negative number are less than 0 are all the real numbers such that x is less than 0. How about non-negative? Non-negative means what? The number that are not negative. So meaning these are the positive number plus the 0. Okay. So similarly, you can define the non-positive. Can you tell me what the non-positive number is? R less than or equals to 0. By symmetry, you should be able to write this down. Symmetry. So I invite you to think one of the things here. So what I told you is some order, right? Okay, some order here that satisfies these things. You could imagine that I can sort the sign of these two. Right? For example, I can say that 1 is greater than 2. I can swap the order. Can you imagine? I can swap the order of the real number line. Then in that case, your usual negative number maybe. And understand what I said? Yeah. Let's say you swap the order. Okay. Small become big. Big becomes small. Okay. Then the positive, negative here would mean different things already. Okay. Does it make sense? Okay, because the order is just something have to satisfy this. Okay, I invite you to check. If you swap the usual positive, usual greater or less than equal sign, you still get these things. Okay. Right. So then in that case, we based on this observation here. So let's check something. So if A is a positive number, then its inverse has to be negative actually. Okay, the additive inverse has to be negative. Okay, so how do we prove this? Well, how do we prove this? So like what we say just now, right? There are three possibilities that this negative A could take. What are the possibilities? Okay, so now you want to make sure it's less than 0, right? So if you compare minus A and 0, what are the three possibility you have? Trichotomy law. What are the three possibilities? Negative A is less than 0 or equal to 0 or greater than 0. Okay, so what do you want in this case? Less than 0. Okay, so meaning you need to throw away the other two possibilities. Okay, so we prove by contradiction. So we prove by contradiction. So we need to throw away the other two possibilities. So let's say if minus A is 0, okay, what could happen here? What can you do to minus A? Still remember the axiom we have last time? The consequence of the real number axiom. Huh? What? What can we do to this equation here? You mean minus A equals 0 plus 0? 0 is less than 0. You mean like less than 0 like that? But then I thought just now we say that 0 have to equal 0, so trichotomy law say that 0 cannot be less than 0. Yeah, so cannot. So what else you can do here? Maybe you can think of this axiom that we can play around. Where's our axiom? No, the consequence of the axiom. Hmm. Set theory, how?
So because thinking A is equal to 0, right? And then
Yeah.
so 0 is in
Real number.
negative number.
No. What? We have to prove that, right? This is what we want to prove, right? We are not using that. So okay, okay, sure. Okay. So again, we come back to the goal and assumption game again. Here is our goal. Okay, here is our assumption. So meaning what? You need to somehow relate your goal to your assumption. Is there a way to make minus A to A? Yes. Multiply -1. Okay, so we can multiply -1 to both sides. Right, again, minus -1 to both sides. And then last time we say is what? Minus A times A is what? Do we have rules here? Yeah, so I mean, like, you can use this to make it this one. Okay, so get minus A, and then minus anything times 0 is 0. We prove it in class right last time. And then minus A minus A become A. A is 0. So here is a contradiction here. Because we say that A has to be greater than 0. Right? Your assumption. So cannot be true this case. How about the other case? What if minus A is greater than 0? What could happen? How do you relate to A again? Yep, good. So we can plus A on both sides. Then you get 0 on one side, and then you get A on the other side. Then this is again a contradiction, contradicting A greater than 0. Again, no matter A is less than 0 or equal to 0, it is not greater than 0. Okay, so by trichotomy law, only case could happen is minus A is less than 0. Okay, does it make sense? Okay. Yeah. Yeah, maybe sometimes you will ask why we have this axiom, why we have this law. Okay, because it turns out it works. Yeah. So far it works. So okay, continue. Maybe I give you exercise, you think about it. I give you 2 minutes. So let's prove the closure of positivity under addition. So let's say if A, B is in R positive, then A plus B also in R positive. Okay, I'll let you prove this. Use a similar method. Or you can think of the other one. I write something down. Okay, let's try. So again, I will prove by contradiction. Okay, so we want to show that A plus B is in R, right? So this is our goal. And our assumption is we know about A and B. So suppose by contradiction that A plus B equals 0, then what we get is A is equals to minus B. This one so far makes sense? Yeah. But then since A is greater than 0, A is greater than 0, then this implies that minus B is also greater than 0 because it's the same thing. But then from previous case, what do we get? If minus B is greater than 0, then what is minus B? B, yeah, it's B, sure. But then B is greater or less than? Greater or less than? You put a negative, you swap the sign. Okay, so it becomes less than 0. Okay, so if you have, so please remember, okay, so whatever we proved before, right, you need to remember we are ready to use it. So if A is positive, minus A is negative. So if minus B is positive, minus B is negative. Okay, so this says that B is less than 0. But then you started with what? B is greater than 0. Okay, so there's a contradiction here. Okay, a contradiction. Okay, maybe I should write in full sentence. This is a contradiction as B greater than 0. Okay, so far okay? Okay, so let's continue. So this is the first one. How about the second one? So next, suppose A plus B is less than 0. Okay, so we need to rule out another case. But in this case here, we get A is less than minus B. Okay, similar thing. So how to do analysis now? Okay, what analysis we had? We know that A is greater than 0.
Yes.
But at the same time, minus B is greater than A. What can we infer here? You see, there's a chain here. When we have the chain here, what does this mean? We can use transitivity. Okay, we use transitivity here. So transitivity says what? Yes. So by transitivity, negative B greater than 0. Then this implies what? B is less than 0. Okay, another contradiction. So another contradiction here. So by trichotomy law, we only left with one choice, which is A plus B is greater than 0. Okay, no? Okay, so we use trichotomy law to prove it. Okay, any questions so far? Okay, so there's another way to prove this. I put it in my notes. My previous student did it. Is you use trichotomy law on your assumption. Okay, you assume A is less than B and then prove it. So you assume A equals to B and then prove it. And then assume A greater than B and then prove it. You can do this exercise also. Okay. So you assume trichotomy law on your assumption and then you prove by cases. Okay, so far. All right. Maybe one exercise you can go back to do is, but we're gonna use it. It's called the closure of positivity under multiplication. Can you imagine what this statement is? Given that you know closure of positivity under addition, you want to guess this statement? Okay, if A, B greater than 0, then AB has to be greater than 0. Yes, prove this. Okay, similar method. Okay, so we're gonna use this to prove this claim here. So the first thing you're gonna know is we have additive identity is 0, multiplicative identity is 1. We're gonna prove that 1 greater than 0 in this case. No matter how you define your greater sign, 1 have to be greater than 0. Okay. So, well, so what are the possibility for trichotomy law? Either equal, either greater, either less than. Okay. But then we already know that 1 is not equal to 0 because last time we said that if they are the same, then our field is just 0, then it's boring field. Okay, so we want to make sure our field is not 1 is not equal to 0. These two identity have not shouldn't be the same. Okay, so we only left with two cases, no? Either less than or either greater. Okay, so we're gonna rule out the case that it is less than. So suppose for contradiction that 1 is less than 0. Okay, or equivalently, minus 1 is greater than 0 from what we know just now. Yeah. Okay, from what we know just now, if you put minus sign, it swap the sign, swap the inequality. Okay, so what do we do next? So we're gonna play with this number 1 here. How to play with number 1? Hmm. Sure, sure. What can you do? 1 times 1. Negative. So how? Sure. Yeah. I think there's not much room you can play, right? Yeah. So you can play with negative 1. Wait, 1. Okay, man. Maybe play with negative 1. Okay. So negative, negative 1, negative of negative 1. Inverse of negative 1. But then I can write it as minus 1 times minus 1, right? But then minus 1 times minus 1 means what? Minus 1 is greater than 0. Two positive number you multiply together, you still get positive number, closure of positivity, okay, under addition. So this is greater than 0. So you get 1 less than 0 and 1 greater than 0 at the same time. So contradiction. Okay, so we get contradiction. Contradict what? As trichotomy law only allow one one inequality to happen. Okay, you cannot be greater than 0 and less than 0 at the same time. Okay, so 1 is greater than 0. Okay, does it make sense? Okay, can you see the usefulness of contradiction here? Hey, why my contradiction wrong spelling? Contraction. Contradiction. Okay, contradiction. So do you see how useful is contradiction here? You introduce an extra assumption for you. If you imagine you don't have this extra assumption, how are you gonna like fight this argument? Okay, so contradiction provide extra argument for use. Okay. I don't know. I cannot imagine how to prove directly. Maybe you can try. Okay, so far, okay. Okay, so now you know why 1 is greater than 0. Okay, so next, the corollary is 1 plus 1 is not 0. Okay, so that the piano axiom actually makes sense. Okay, the plus 1 should get you something different. Okay, if 1 plus 1 is 0, maybe our world is a simple world. Yeah. not much number you can play on. Okay. So corollary, 1 plus 1 is not 0. How to prove it? So definitely we need to use the fact that we know 1 is greater than 0. Okay, so how are we going to use it? Yeah. Sorry? Sure. Okay, so maybe we can play around with it a little bit. So since 1 greater than 0, 1 plus 1 is greater than 1 or greater or equal than 1? Look at your law. If you want to, so add 1 both sides is what? The order preserving property, right? So let's go and check. Okay. So you have this condition, right? And then you want to get this. Yeah, but this is only with less than or equal to. Okay, so you need to be a little bit careful. So just put less than or equal to, because there are some cases that it could be equal. Plus 0, then equal, right? Definitely. But then maybe there are some exotic cases. Okay, so you have 1 plus 1 greater or equal to 1, but then at the same time, we know that 1 is greater than 0. Is it possible to use transitivity here? Is it possible to use transitivity here? So we need to be a bit careful, huh? That is, this transitivity here, just concerning less than or equal to. That means that this part here actually need to be proven for this part. Which part? This part. This transitivity here. Okay, why it fall for the strict inequality? Okay, maybe I think we should put a lemma here. I will write it in the notes. So lemma here. If A greater than B greater than C, then A greater A strictly greater than C. Okay, maybe we need to do this lemma, but then let's do the lemma here first. Okay, so we'll prove a lemma here. If A greater than or equal to B greater than C, then A greater than C. Okay. So why am I doing here is because in your previous axiom, right, we have this equal sign here. Okay, but then we remove this equal sign. Okay, does it make sense? Okay, can you see the difference? Can you see the difference or not? Okay, so we need to address this difference. Okay, so let's prove this. What we know from our axiom is this. Okay, so proof of lemma. So what we know from the axiom is by order preserving property, we know that A is greater or equal to B, C. Okay, so what we want to rule out is A cannot equal to C. So what should we do? If we want to rule out A is not equal to C, assume equal again. Okay, so suppose by contradiction. So suppose on the contrary that A equals C, then A is greater to B implies that C. Okay, so okay, sure. So we know that A is greater or equal to B, and then what do we know? Because A equals to C, right? So since A equals to C, then we also know that C is greater or equal to B. So what does this imply? So this implies that C is greater to B or C equals to B. Can it happen or not? Why? Trichotomy law, yeah, and then what else? What do we know about C and B? Yeah, so we know that B greater than C. None of these is B greater than C. Okay, so that cannot happen. Okay, which both contradict B greater than C by trichotomy law. Okay. Okay, so that's why you can be sloppy. In future, you can be sloppy whenever you see this greater or equal or greater, then you can deduce greater. You cannot deduce greater or equal, right? We prove it to you already. Cannot be equal. Okay? But then if you write it as a logical statement, you still can write greater or equal to, right? Although you know that equal is false. Does it make sense? You get the logic? Okay, although this is true, but we still can write greater or equal because or you can or with a false statement. Does it make sense? Okay, but then what is true is strictly greater than C. Because I think in this case we want the strictly greater, I guess. Yeah. In this case we want strictly greater. So therefore, if you apply the lemma, 1 plus 1 greater than 0 implies that 1 plus 1 is not 0. Okay, does it make sense? Okay, so by trichotomy law. Okay, any questions so far? Question? No? Okay. So 1 plus 1 is not 0. Okay, good. Okay, so let's continue. So in this case here, we will define, so how going to define this greater or equal signs? There's few way to do it. Okay, there's few way to do it. Either you define the sign of order, or what we're going to do now is we can define this way. So we could define A is greater than B if their difference is in some positive number that you define. So meaning what? You just define what is greater than 0, what is less than 0, then everything will get defined. Okay? Yeah. So you don't need to define for every number, but I mean every pairwise number, but then you just define a number, what's the relation of the number with 0. Okay, so let me write down first and then I'll draw you a picture. So I will define that A less than B if the negative of A minus B is living in the positive number. When I write this down, I try imagine using your previous experience. Does it make sense or not? Okay, if A greater than B, their difference have to be positive. Okay. Although we can abstract it, but try to think using your own way. I mean your previous experience first. It should match up with your previous experience. Okay, so what am I doing here is, if you need to tell like A is greater than B, okay, so you just compare their difference with 0. Okay, you just compare their difference with 0. Okay. You just compare their difference with 0. Okay, so far. Okay, so you just compare your difference with 0. Okay. All right. Next, we define what is modulus is. Okay, modulus is a very important definition in analysis. A lot of function will define using modulus. So modulus of A, meaning you will get A if A is greater or equal to 0, or negative A if you get A is less than 0. So this makes sense, right? This notation here. Or I would say that R is A is living in A R is greater than 0 or A is living in R less than 0. Okay. So what does this modulus do? Modulus is kind of like taking the length of A from 0. Okay, what's the length of it? Huh? The length. What do you mean by value? Yeah, we call it length. The length. That, in mathematics, we call it length. Yeah, the 那个长度. We think of it as a vector actually. Magnitude also works. Physics will always use that. Yeah, physics. Yes. Actually, yes. Real number, there's a geometry on real number or topology on real number. Yeah. We prefer length more than magnitude. Magnitude is like physics term. It's okay. Magnitude also can. Value, less precise because there's a lot of different value. But then previously. Yeah, it is called absolute value. Yeah, it's called absolute value. Yes. Yeah, it's called absolute value. But then the idea I want to instill you is this absolute value give you a length of a number. Give you a length. Length should be positive, right? There's no negative length. Right? Huh? Or maybe one day can. Maybe quantum physics can. I don't know, but then we can go backward in time. Okay, well, so there's another story. Next, let's talk about properties of inequalities. Since we have defined these inequalities now. So let's take 3 numbers from R again. First is if A less than B and C less than 0, then AC is greater than BC. Okay, so this is the swapping property by negative number if you multiply. If 1 greater than 0, then negative 1 is less than 0. I think this one we see it already. Okay, but then you should prove it. You should try and prove it. If A greater than 0, then 1 over A is less than 0, right? Oh, you still greater, sorry, still greater. Yeah. If 2 greater than 0, 1 over 2 is still greater than 0. Yeah. You didn't solve it. Okay. But then if you have A less than B, but then both of these are greater than 0, then both of them still greater than 0 after taking reciprocal. So this is what we call taking reciprocal, right? But then 1 over B will be less than 1 over A. Okay. And then finally, the famous triangle inequality you cannot forget in this class is the absolute value of A plus B is less than or equal to absolute of A plus absolute of B. Okay. So this one says what? If you add two numbers together, you measure the length, it has to be less than or equal to the sum of separate length. Does it make sense to you? When can it be strictly less than? You think of some number and make it strictly less than. Yeah, sure. So maybe you take 2 plus minus 1, right? So on one side you get 1, the other side you get 3, strictly. Okay. So there's a reason why we put a less than there. And then the other triangle inequality is sometimes we call a reverse triangle inequality. So this one is very special. It works in some case, might be useful. So if you take the difference of two lengths here, and then you measure the length again, this should be less than or equals to the length of A minus B. So 6 can be proven by 5. Okay, so let's see which one we want to do here. Okay, I prefer doing 1. I prefer doing 5. Anything you interested? Everything? Okay, we cannot accommodate that. Not much. Not enough time to do all. But then second one, I think we did it before already. No, you can only pick one. More. If not, then we will do this too. Huh? We cannot do everything. Huh? What? Oh, I mean pick exactly one. Yeah. The other were left for exercise. Pick one more. 6 ah? Okay. Sorry? It's choose 6, there's no reciprocal for proving. Okay, I think you have a very good sense. So maybe we can vote lah. So do you want to vote between 4 and 6? Huh? Do you mean 4? Okay, pick one. You pick one first, then we vote. 3, huh? Okay, so let's vote between 3 and 6. Huh? So which one we want to do? So who want to see 6? 6 first. Who want to see 6? 2. Okay, 2. 3. Okay. Who want to you can do multiple vote, huh? Who want to do 3? 3. No one want to do 3. Okay, then we do 6. Huh? Okay, so we'll do 1, 5, 6. Huh? How about we do it after break? So come back at 10:02. I think, hello, testing. I think starting from today, you don't need the generating code to sign in, right? You want to try for the online? Yeah, but I'm not sure I need to start or not. Maybe I need to start first and then you don't need to sign with code anymore. Let's try. This is what I see from the email. Can you sign in? Season better, never mind. I also cannot sign in. I think IT is a job here. But luckily, this same Moodle is okay. Moodle become okay, then this thing become. Then I'll take attendance here. Zhang Henyu, Dan Junhan, Chong Yuheng, Liu Chunxian, Chunxian, Chunxian啊，oh here，俊贤咩？不是春仙，俊贤啊。OK，好，没有在啊。OK，男的女的？男的，对，瘦瘦的。哦，我记得了，我记得了，我记得了。OK，他在哪里？睡迟了。好，还在睡觉。OK，他昨天在什么？好嘞，开自学好，这样我就不担心了。安徽界，安君卫，你们两个有亲戚关系吗？没有，姓安的哦。昌金庆，昌吉庆，sorry，昌文卫，清康义，林一행이 행百姓杨，林宏杰，宏杰没有字。Bravely no，文冲称卫，哎，你上个星期做什么？睡死了，哇，睡3天。OK，下次把船带过来。OK，邱优炫，OK，Helen Lee，翁宏俊，霍永顺，修思慧，天乐，捞祁阳，OK，也平杰，刘昌，袁浩，OK，李晨玉，OK。Anyone didn't I didn't call your name. I think I haven't assigned your assignment, right? Wait, let me see. So your revision week, I think I already assigned for you. If you want, you can start typing already. I think more or less the same sequence that I did last time, but then I think I'll add something or I will adjust a little bit, but it will be minor. So let me show you what you need to do. Okay, I already assigned you a schedule here. So here's your schedule. Okay, so this is the week that you assign to. Anyone, your name is not on here. Is your name not on here? I put on the course info, you can find it in Moodle. Anyone, your name is not on here? I need to check again. Okay, so if I assign you to any week by lectures, because we did one lecture advance last week. So you need to type them up. Okay, type the lecture up. And then what else you need to do? Let me see. Right. So type the lecture and then if can make some summary. Okay. And then I want you to find some question to do. Okay. The student very smart one nowadays. my students input lecture notes to Gemini or ChatGPT, output 100, 500 quizzes to do. Can one? Okay, go and do it. So go and find question with solution, one true false question, and then one constructing example question, and then one proof question. Okay, go and do it. Practice yourself. Yes. Can. Why not? But then don't like out of syllabus. I want to answer using the syllabus here. Can. Textbook also can. Make sure the solution works. Don't simply make up some random false question. And then write down your reference. Okay. Yeah, textbook is a very good place to find it because I have upload a lot of solution manual, right, to different textbook. Yeah. Do it. Please do it. Yeah. Please try them. Okay, so far. Okay. Yeah. Okay, so this will help you to do revision. Hopefully this become your habit. Okay, it's not just this week is me doing, oh, I only do this week. Then other week I don't need to do. So it's just like training to you. Okay, yeah. But then I will share your notes to the rest. Okay, so that can help people to study. Yeah. So if can, please, for example, if you are doing week 2, right? So week 3, you submit your stuff. Okay, but then I'll give you chance to edit them up to the end of semester. But then you submit the kind of draft first. Yeah, so that people can study together and then give you feedback and then how to make it better. Does it make sense? Okay, so after each week, you submit your draft, submit your lecture content, submit some question, okay, that people can try and do. And then I will ask you to submit a final one at the end of the semester. Okay, but after each week, please submit one version. Does it make sense? Okay. Yeah. So help you to do the continuing revision study. Okay. 来督促你们学习。Okay. Any question? All of your name is here. I didn't miss out any of you. Okay. Please let me know if your name is not here. If you miss out this assignment, it will be quite a few marks to lose. Okay. So let's do it one by one now. Okay, let's do the first one. Okay, maybe Pingjie was worrying about the taking reciprocal, right? Maybe there's some advice I can give you. Taking reciprocal in multiplication is kind of taking negative in addition. You understand? Because reciprocal is like taking multiplicative inverse, right? Negative is like taking additive inverse. So these two inverse have similar effect. Yeah, so you can think of how you prove for the additive inverse. Yeah. Okay. So let's do the first one. Well, so let's write down what we had and then write down what we want to prove. So for the first one, suppose that A less than equal to B and C less than equal to 0, and then we want to show that AC greater than BC. All right. So what can we do here? Hey, sorry, sorry. To remove this. Okay, so what should we do here?
Assume that EC is equal to BC.
Assume. Oh, you mean the trichotomy, huh? Okay. Let's try that. I'm not sure it works or not. So let's try. So you want to assume for contradiction, huh? Okay, you want to use transformation. That's not what I wanted to do, but then we'll try this. Then sure. Okay, so since C is not 0, right? So C inverse exists. Okay, so by cancellation law, A equals to B. You can cancel C on both sides. So multiply C inverse on both sides. So which is a contradiction? Contradicting A less than B. Okay, good. We still need to draw another case, right? If you want to use trichotomy. So what's the other case? Again, assume for contradiction, AC less than BC. Okay. So what do you do next? Do we have that? Do we have that kind of property then? So you try to like cancel out the C, right? So it's like using proposition one, right? You want to multiply C on both sides, something on both sides. Yeah, the problem here is we don't have anything to do with cancellation law if it is a straight inequality. We want to prove something like that. How? Can proceed? If not, we left Qi Yang to think about his solution. Think of it later. Got idea, Qi Yang? Haven't yet? Okay, I'll let you think about it. Okay, if you can settle this case, then we are happy. But then how about we use different way? So we're gonna use axiom again. So let's use the other way. So by proposition before, C less than 0 implies that negative C greater than 0. Then we can use order preserving. Maybe this will give you some idea. We use order preserving property here. What do I use here? So A times minus C should be strictly less than B times minus C, which I get minus AC minus B less than minus BC. So I think there's a hack here. There's a hack here. Did you see what's the hack here? What does the order preserving say? Let's go back again. Recall what we have in the previous hour. We have strictly less than or equals to, right? Strictly less than or equal to. So just now I just put strictly. Okay, so you can prove a similar lemma. Can you throw away the equal sign? Basically, it's what we did just now, right? With Qi Yang just now. Okay, so we can throw away the equal sign. But then I think this is what Qi Yang needs, right? Do you need this? Maybe you can use this. Or Qi Yang needs C inverse, huh? You need C inverse, right? Do you need C inverse?
Sorry.
C inverse, you need C inverse, then you need to prove the second line already. You need to prove the second line. I'm not sure. Okay, you need the third line. Eh? No, wait. Yeah, you need third line, right? You need this third line here.
Highest order.
Need this. Yeah lah. But then you still need this stuff. You still need this one so that you can use negative C. Okay. I'm not sure 3 need to rely on 1 or not, but then you can try if 3 doesn't rely on 1. Okay. So is everyone okay with here? This is not equal. Maybe you can make it a lemma here. Okay, but basically it's what we did here actually. So it's not equal, it's less than. Then is this what we want? Negative AC less than negative BC. What do we want? AC greater than BC. So what can we do next? Do you see a difference? Okay, maybe I write down the goal here. So the goal is AC greater than BC. Okay, so how do we proceed? How do we proceed? Huh? What do you mean I take difference?
Difference of
Difference of both sides?
AC, right?
So what do you mean by that?
See, it's positive.
Right. So by doing that, actually, what do you do actually? So you are just adding like AC or BC to both sides. Yeah, yeah. So by doing what you say, you are checking the whether it's positive or not, right? So by doing that, it's just like what you're saying is equivalent to do adding like BC and AC to both sides. To both sides. We get BC less than AC. Okay. Is it equivalent? Okay. So maybe you say take AC plus AC on both sides. Okay, so you want to check like whether AC minus BC is greater than 0 or not. Yeah. Right. Yeah, somehow. Yeah. But then yeah, right. But then this line, if you add AC to both sides, then what does it say? AC minus BC is greater than 0. So if AC minus BC is greater than 0, that means that AC is greater than BC. Yeah. Okay, good. Yeah. Okay, so maybe I need to apply another lemma here to get rid of the equal sign. We want strict, right? Yeah, we want strictly greater. Okay, makes sense. Okay, so in this class, you need to be very what we say is meticulous. Qian, what is meticulous? Hey, your English so good. Hey, meticulous, you need to be very super careful. You need to be very super careful. Super careful means what? If I say less than or if I say equal or less than equal, these are very different things. So you need to show that it actually works. Okay. So if I remove any equal sign or strictly equal, they are really different. Sometimes they are okay, sometimes they are not okay. So you need to be very careful whether I write equal or less than equal. Okay. Okay, good. Right. So this is for this, and then let's do the next one. What's the next one? Number 5. Okay. This is the boss. All right, let's do the number 5. Number 5, we will rely on one very special lemma here to make things easy to say. So if you have any positive number and some natural number, if A less than B, if and only if the P power of A is less than the P power of B. Okay. Think of it, first of all, does it make sense or not? If 1 less than 2, and then 1 to any power, and then 2 to the same power, is it grow faster? Is it still growing faster or not? Kind of makes sense, right? Okay, so how to prove this? Yes. Huh? Oh, what is power? Very good question. Okay, very good question. So power is defined to be multiplication p times. P times. Correct? 2 square, 2 to the cube. Correct or not? P times. Okay. Multiplication p times. Okay, so what's the proof? Well, I think we will use the binomial expansion. Okay, what is b P minus A. P was the formula. Well, you can factorize B minus A, okay? And then the something left is B to the P minus 1 or to B to the P minus 2A plus B to the P minus 2. Okay, so how do I figure out this? Maybe I ask you to expand it first. Do you get this? I mean, do you can check it? So one way to quickly calculate this is you open up bracket, right? So B times this chunk of thing, what do you get? If it is like you translate the B up by 1 power, right? You B multiply everything here. So you get the BP first, B to P first. And then the rest is just B to P minus 1 with A and then up to B times P minus A. And then how about this bit here? This minus A here exactly help you to cancel out this chunk. Can you imagine or not? Maybe we do a smaller exercise. Okay, so also another technique in this class is if you want to check for this like large number, right? You can verify in a small number first. Let's say is this small enough? Or is this troublesome? Let me write down first. Like that. Okay, so what do you do for the first line of multiplication is you translate everything up by power of V. And then the second line is you will produce minus A cubed first of all, and then the rest will pick up B squared, BA with an extra minus A. Okay, so they will cancel out. Okay. Minus B squared times A minus B times A squared, and then here is minus A cubed. So these cancel out, left with what you want. Okay, yeah, so this is you can treat it as a formula. Okay, so in this case here, then what? Then what did you see from here? How do you compare BP minus AP and B minus A here? So remember, what's our assumption? Our AB is always positive. Okay. So what's in this chunk of bracket here? Positive number times positive number. So just now we say that positive is under multiplication, we have closure of positivity. Positive times positive still positive. So this whole part here is always positive. Okay. But then what is B minus A then? What do we assume here? B is greater than A. So B minus A is also positive. So positive times positive is positive. Okay. So then B minus A is positive, implies that BP minus AP is also positive. Okay. Make sense? Okay. So I can go backward as well because that term is always positive. If you are positive, then this term should be positive. So actually you can go backward. But forward is what we wanted. Okay, so far okay? Okay. Okay, good. So in this case here, what we're gonna do is we're applying a lemma with p equals 2. Okay, so for example, we have two number greater than each other, right? Greater or equal to. But then we can actually take square on both sides. You can take square on both sides. Okay. Well, how do you square? How do you square? Okay, on the other side, I think this is obvious, right? This is just this square plus this absolute value of 2 times absolute value of AB plus absolute value of B squared. But then this turn how to square? This turn how to square? What do you mean by definition? You split into two cases. Okay, makes sense. Okay, you can do that. Okay, but then, I think we could do something like this. we can prove another lemma. There's another lemma, huh? Okay, maybe we can do something convenient first. We will show that absolute value of a square should be equal to a square. Let's prove this, and then we will easily throw away the absolute value sign. Okay, how do we prove this? Like what Kendall said, you have to use the definition of absolute value. Okay, see if both cases correspond to the same thing or not. Okay, so we know that absolute value of a is a if a greater than 0, equals 0, negative a if a is less than 0. Okay, so two cases. Suppose a greater or equal to 0, then absolute a square is just a square. Done. And then the other case, on the other hand, suppose a is less than 0, then absolute a square becomes what? Negative a square. Again is a square. Done. Okay, makes sense. And then this is actually what your calculus teacher tells you, right? We define absolute value as square root a square. Isn't it? This is what you learn for absolute value. Do you see? Do you see this definition before? Square root a square. I think my high school teacher say this. Not my calculus. No, man. Your high school teacher didn't tell you. Then did you learn about absolute value before? Then how do you learn about it? Make it positive. Okay, okay. Okay, good. Sure. Another way is they write it like that. Square root of a square. After you square, then definitely you can take square root. Okay, cool. So what do we have here? So I can throw away the absolute value. I just say a plus b squared lah. So here I become a squared plus 2ab plus b squared. And then on the other side, I also just get a squared plus just keep the 2 times modulus a, just b plus b squared. So what did you see here? So I can cancel a squared, b squared from both sides. And then what do I get? 2ab is less than or equals to 2 times absolute value of a times absolute value of b. How about this? How about this? Should we prove this? Can I stop here? Which is always true. Not happy. Not happy. I think if you are not happy, then I'm very good already. So meaning, how many cases you need to show here? I think there are 4 cases. Yeah. Definitely. But then okay, before we showing the 4 cases, let's think about it first. So if everyone is positive, then should be fine, right? It's just 2ab equals to 2ab. Correct? Huh? What do you mean? Yeah. Definitely. If it is positive, this is just A, this is just B. So 2ab equals 2ab. So this line is correct. If it is both negative, so you can write it as a negative of something. So negative of A, negative of B, let's say. Then here become AB, right? But then the negative here can cancel. Again, 2ab equals to 2ab. So the problematic one, I guess, is the one positive, one negative. Okay. So if it's one positive, one negative, here will always be positive. Understand? So this side become a negative number. This side become a positive number. That positive number is greater than 0. 0 is greater than the negative number. So transitivity says that positive is greater than a negative. Okay. But by right, you have to show the 4 cases. Okay. In that sense, let's make it into lemma. Okay. I'll write in the notes. Okay. Okay. I can get the idea. Yeah. Okay. But then to write it out, you need to split into 4 cases. Cool. So this is it for this part. Can I say that for 6, you do similar things? 6, 6 actually you really do similar things. Yeah. Sorry. Yeah. You okay? You want to proceed with this? Okay. What do you do? What do you do? Wait. Let me leave some spaces first. Okay. Let's continue. Yeah. From this line.
You know that is less than B, right? And as per question, I mean, as
Oh, okay. So yeah, sure. So we know
minus B less than 0.
we know that A less than B, and then
B minus B less than 0.
okay. So this implies that A minus B less than 0. Yeah, sure.
Yeah, I skip one step up here. Then,
Yeah, you skip one step, sure.
and
Yeah.
then so negative A minus B is greater than 0.
And actually, what we define is that one. Actually, what we define is negative of A minus B is greater than 0. This is what we define. So you can jump straight to here. This is how we define this less than. Negative C. Okay, so we also know that. So we also know C is less than 0. And then this implies that negative C is greater than 0. Okay, good. Multiply them together.
So we assume AC less than BC, right?
AC minus.
So AC minus BC less than.
So also moreover or beside. A BC minus AC equals 0, or which one you want to use? Okay, so you want to use the minus version. Minus of AC minus BC is greater than 0. This thing? Is this what you want to use?
I said AC
Ah.
minus BC less
AC.
than.
It's the same thing, right?
Yeah, same thing.
Mm.
The assumption.
And then
I also said A minus B whole thing and C less than 0. So
what's the next step?
I also said A minus B whole thing and C less than 0.
Distributivity. Okay. I was thinking like where's the so by distributivity A minus B times C less than 0 like that. And then
And just do a lot of steps. Get negative the whole thing A minus B times negative C less than 0.
no need a lot of step, right? Oh, okay. A few step, actually. So you put a negative here, and then you commute, and then you yeah. Okay, sure. So this will implies that okay. So Chiang said a lot of step here. Definitely, there's a lot of step here. You need to like create a minus one, and then you associate, you commute, whatever. So you get minus A minus B times minus C less than 0. Okay, and then
B minus B is
positive. Good. Okay. So here there's a contradiction already. Where's the contradiction? Here there's a contradiction already. Because you know that minus C is positive, minus A minus B is positive, and positive should be positive, but you get something negative. Okay, so there's a contradiction. So contradicting minus A minus B times minus C should be greater than 0. Okay, good. Can. Yes. Yeah. Okay. So see, there's a lot of way to solve a problem, but then if you compare this way, right, you should think like which one is faster. You need to imagine you write in the exam time. You can do whatever you want, but then you should see like which one is faster. Okay, when you do these exercises. Okay. Question 6. Question 6 pula. Yeah. The reverse one. Can I say that it's the same as angle inequality? Do you buy my argument? You want to let me think first. Let me see how I convince you. Yeah. But claim proof, ah? You mean claim proof for triangle inequality or reverse one? The reverse one. You want to share? How about you share here? You share here. You come here. You come. How clean? 5-line proof. How clean? How clean is it? How many lines?
How many lines? Not two.
How many lines?
But there's one lemma that didn't destroy.
Yeah, you see there.
So basically,
Oh yeah.
they must have gone. They must have.
Yeah, that's wait. Oh, 对哦 unless you have this I'm not going to use that, but then sure you need to do that first. Okay, sure. Okay, there are two ways. To do this question here. 6. One way is to use similar proof as 5, or you need to establish something extra. So this is the first method, or method 2. So this is method 1. Use the power thingy. Method 2 is you need to establish this lemma. I think this is what you know from high school as well. What is that? Is it if and only if that thing? I feel like if only. If then can is used is enough lah. Yes. Wait, say again. So T, wait, let me think. So which one is true? So modulus of A is less than or equal to T. Like that? Yeah. You know this, or did you know this? Yeah. Okay, sure. But then this lemma is very useful. I think sometimes in the proof we need this as well. How about without proving you the triangle inequality, reverse triangle inequality, but I prove this for you. For this, I give you the tool that you go and use yourself. Is it okay? This tool is very important actually. This tool is very important. Let's prove this one. This is pretty important. So how should we start? Where should we start? Huh? Got 3 meh? Not just 2 meh? Why got 3? Oh? No lah, no need lah. You just care about this man, right? This is your goal, man. The goal is this guy, man. This guy is defined piecewisely, so you need to treat it differently for different case. Okay, so this is your goal. Goal is here. Okay, so we want to show that. So write down your goal every time. Okay, the modulus of A is less than 50. So then, by definition, so if A is greater or equal to 0, then we want to show that modulus of A is less than T, or equivalently, A is less than equal to T. But then, kind of obvious, right? But which is true by assumption. Fair enough. Assumption already tell you that this is true. Okay, so for A positive, it works. How about the other case? The other case is A less than 0. Then what do you want to show? Then we want to show that modulus of A is less than or equal to T, which is equivalent to minus A is less than or equal to T. But then this is again assumption. Okay, so actually what it says here is just we try to unroll our definition only. Okay, we just unroll our definition. Okay, does it make sense? Okay, we're just unrolling the definition. Is it okay or not? Do you like confused 啊？打结啊嘛？有吗？你的脑有没有打结？希望你没有打结啊。如果有打结的话，你跟我讲一下，我帮你打开啊。I'm doing not theory by the way. You know what is not theory? You know what is not theory? 有听过吗？Kind of topological stuff, but basically it's like 现在人没有穿包鞋了哈，不穿拖鞋了。包鞋 yes, very few 啦，包鞋 right. So when you tie it out, right, tie your notes. Okay, so we are like try to distinguish what notes is equivalent to each other without opening out the notes. Yeah, without opening out the notes. And then, well, I mean, you can use topological way, like meaning you twist it, whatever, without breaking the string. But then the other way to do it is we can use algebra. We can use algebraic way to see. This is what we're gonna do. And then to distinguish knot is what we call invariant. Yeah, so if those two knots can be make the same, so meaning you don't break it, but you can try and play around with the string. If they are the same, they should have the same invariant. It's like a name tag for the name tag for the knots. No matter how you cut your hairstyle, you are still 拼接嘛. Okay, so here we are just basically unrolling the definition. Okay, nothing much. Okay, but this is very useful actually. Yeah, I think calculus uses it a lot. Analysis, we will use it super many times. Okay, so far so good. I think there's another one, right? There's another one if you still remember. There's another one about this absolute value greater than t. You can show it this is equivalent to what? You still remember this inequality here? T is, so A is greater than T, or T is less than or equal to minus A, right? Right. I mean, how do you remember this? I don't think you can just memorize. Okay. I encourage you to think of a picture. What's the picture you need to think about? I'm not sure your high school teacher teach you or not. A good high school teacher will teach you. So, what is absolute value of A less than T here? So your T should live in between A and minus A, right? Okay, so this is the part that T can live. Correct? Is that true? Am I drawing the wrong stuff? T, I think I draw wrong stuff. Is T greater? Let me see. Let me see. What am I doing here? Wait, let me think. T is greater. T is an interval, right? Let me think. What's the interval am I drawing here? T. Did I wrote something wrong here? Sorry. T minus T plus A. Oh yeah, sure. Wait. Let me think first. You mean plus a T here? Did I draw something wrong here? Let me think. The absolute of A is in between T. So the length here should be at most T. So did I wrote something wrong here? T here, let me see. T greater than A. So okay, let's draw what I say here first. So A here minus A. T is here. T shouldn't be here, right? So there are two cases, either here, either here. Okay, so let's think about this. So you sure this condition is correct? Let me check. So A less than T, let me sure that T is greater. Seems very weird, huh? So A less than T, make sure that this less than this. A is great. Oh, okay. So let me write down something here. So what the one I wrote in yellow is false, right? Yeah, I think it's false because something wrong here. Okay, well, can I rewrite this? Can I rewrite this? So this implies that yeah, let me put here first. Okay, so let's disregard this first. Okay, let's look at our purple case first. So what's this purple case do? I think this is not the form that you know, right? This is not the form you know from high school, right? From high school, I think we rewrite this as this. So I think we rewrite this as t less than or equals to a and then less than or equals to minus t. This is the form that we know. This is the form that we know. But then actually from here, you can go here, right? You multiply minus on both sides. So actually, this labeling here is not a. You should use t. So your a is in between minus t and t. Okay. Yeah. And then if you swap this, then you will get a greater than t, and then
your yellow one got a negative sign in front of the.
Yeah.
Yeah, I think there's a negative sign. Or for the right condition.
no me. Yeah.
Leave the purple to me, but the yellow.
Why? I already swapped the sign. I already swapped this sign. So it's absolute. I think it's a. Oh, wait, let me think.
You substitute A equals 3t equals to 2, and then you tell that it's not.
Second.
When A equals 3t.
When a equals to 3, t equals 2, then this is yes. Should I put a O here? Put an O here. This is an N, huh? I think this is the N. This is an N because both of them have. But then not really. Not really, but you say your example again. Say your example again.
Negative for yours A. Whether they are put it.
Then what do I put for N? What do I put for N?
3.
3, okay. Yeah.
2.
2, okay, good. And then you say that which one doesn't work? 3 greater than or equal to 2. Good. You said this one doesn't work, right?
Yeah.
Okay, I put an O here. Seriously, this is how it works. Because there's some cases this true, this false. You don't think of it. You think of it. This true, this. But this is still true. Just now you are true, false, right? How about true, false, true?
A equals to negative 3.
A equals to negative 3. And then this one still 2.
T equals to.
Still 2. Yeah, okay, I think works. Yeah, still works.
And then, but the E greater than or equal to T is something.
Negative 3 is become 3, right? 3 greater than or equal to 2. True. Correct. Yeah. I think it's an all here. I think it's an all here. And then this corresponds to this case, this case. Either you live on that side or the other side. Okay, very good. Right. So we have 2 minutes left. What should we do in the 2 minutes here? Maybe I give some. Okay, I'll try write down these proof for 6. Maybe you can try practice yourself also. But then if we have question, if you go back try still cannot, then we can do it on the next class. But then before we go, let's brief you on what we're gonna do next. Because the next part is really the germ of this course. Okay, it's really the germ of this course. So the next part we're talking about bounded set. Yeah, a bounded above set. So if you are bounded above, that means there's a largest number that control your set. Okay, that largest number could be inside your set or outside your set. Later I will show you why it can happen. But this number is what we call upper bound. Okay, is what we call upper bound. And then we're gonna use this idea of upper bound to build our real number. Okay, so what is the slogan here? Let me see. No Kochi? Yeah, it will come soon after I introduce sequence. No worries. Okay, so this is the germ of this course, completeness axiom. Every non-empty subset of real number which is bounded above must have a least upper bound. Okay, this is how we build our real numbers. So if you take any subset of real numbers, you must find some upper bound and it has the least upper bound. This is the part of real number. Cauchy sequence will come later, no worries. We will show, I'm not sure we will show their equivalence or not, but then, yeah. Okay, so the idea is, what is it? First, is some, and not any subset of real numbers that's bounded above, we can find the least upper bound. This is real number. Right, this is completeness. From here, we can prove the structure of your numbers. Later, we'll see something called the density of rational or irrational. So how the rational and irrational sit beside each other. Okay? Yeah. This is just an idea, but we will slowly see what happens. Okay, okay. Yeah. All right. In that case, we'll see you tomorrow.